Welcome to the tutorial 1 of this course Reinforcement Learning. I'm Avik Kaur from I'm a PhD student at Indian Institute of Science. So we'll try to keep this tutorial session as much interactive as possible. So the first thing I'll ask you is, can you please one by one, can you please tell me the topics which are covered in the first week of lectures? So can any one of you please volunteer? You don't have to tell all the topics. You just name few topics and then someone else will tell. Someone is saying something. I cannot infer anything.
So we started with second.
Yash is speaking something. Okay, yeah, tell. I couldn't hear
Sir, am
you.
I audible?
Yeah. Yes.
Yes, sir. I'm saying that we started with a basic introduction of speech learning.
Basic
Then we-
introduction of reinforcement learning. Nice. Then
Yes, sir.
We also discussed with, I think, immediate reinforcement learning.
yes. Okay. So first, reinforcement learning. So I'm just writing the terms you were throwing. So we'll refer reinforcement learning in the course as RL.
We're also introduced with bandit problems.
Okay. So Bandit, what did you study?
Yeah, in the first week, bandit problems is there.
Okay.
So we just covered some basic idea of the optimalities regarding the band.
Okay. And that's it, right? There we have ended week 1. Is it? Or did you study any algorithm?
Sir,
Just
we
an
studied-
introduction to algorithms.
Okay. Yeah, right. So this course is, in my opinion, is quite topic heavy. So what I'll do is I'll try to cut the clutter if there is any clutter at all in this tutorial, and then we'll solve some previous year's assignment problems. And if you have any doubt, you can ask me in this session. So let us start with the basic thing. What is reinforcement learning and why this bandit that is not exactly reinforcement learning as it seems, because that has a separate name, and why studying bandits helps us, and what is the similarities, dissimilarities between these two setups. That we'll look at in the first half of this tutorial. And in the second half, we are planning to solve some questions. So today, for some technical reasons, I may not continue for 2 hours. Let's see. So the first, we'll discuss this reinforcement learning setup and bandit setup. We'll try to discuss without any examples. I mean, there are lots of examples I think we have already seen in the lectures. So we'll just keep the discussion mathematical. So in reinforcement learning, we start with something called, okay, let us draw two parallel bandits, or let us write the full name that we'll discuss. The setup we'll discuss is called multi-armed bandit. Alternatively, I mean, in abbreviation, we call it MAP. And then there is another setup, which is Markov decision processes. So one thing is learning for multi-armed bandit, and another thing is learning. I hope you were already uh, exposed to just a second. Yeah, you are already exposed to what learning is. So another thing will be learning for Markov decision process. So typically, the RL problem, the system, there is an underlying system for which we are learning, and that system is modeled as Markov decision processes. It's not mandatory that it has to be modeled as Markov decision processes. That can be modeled as anything, any other models like linear models, any kind of non-linear models. But this is the most one of the most general one that we study for. And there is another setup that is multi-arm bandit. Okay, so in multi-arm bandit, we have the action space, and we have a reward function mu, which maps from, anyone wants to answer? Reward function is a function, right? So what is the domain and range of this function? Anyone? I think you
So
know that.
domain is the set of actions.
Come again.
So domain is set of actions,
Domain is set of actions. Good.
and the expected payoff should be the range.
I couldn't hear.
So the expected payoff would be the range of the function.
Expected payoff. So expected payoff is what kind of thing? It's a scalar, right? So it's functional from action space to reals. Yeah. So what you do is, for time, or just denote, t equals to 1 to capital T. We have a name for capital T. So capital T is horizon. The agent or learning agent, you can say, if the problem is learning problem, agent plays action at is basically the action we are taking at time t. Okay, so here is one I mean, terminological ambiguity that could happen. Arm, we are saying arm and action, right? Two terms, but they mean the same thing. Okay. So we'll interchangeably use those terms, arm and actions. So agent plays, let me say arm 80, and environment, or the bandit set environment, returns reward RT. So what is the goal here? Goal, general goal could be from t equals to 1 to capital T, we are incurring a reward. So sum of reward, the agent may try to maximize it. So maximize the sum of t equals to 1 to capital T RT. But now let us see what is the other thing, Markov decision process, that is much more complicated. Let's see what does that say. So Markov decision processes has lots of variation. I mean, there are, so I'm just naming it. You may not, I mean, you need not to remember for the time being. So there are finite horizon Markov decision process. There is discounted Markov decision process. There is average reward Markov decision process, and so on. So for the time being, we are only discussing finite horizon Markov decision processes. So finite horizon Markov decision.
Be still and immobile.
Anyone wants to ask some question?
Body still, eyes are still. The mind is becoming still. Keep on relaxing.
Siddharth Sahu, you're speaking something. Is it to us in the class, or is it by mistake? Okay. Okay, I have muted you. If you have any
Hello.
question, you unmute yourself and ask.
Excuse me. Hello,
Yes.
sir. This is Jitendra. Actually, I'm from electrical engineering background. So I request, or either you tell me the some prerequisite course to, if anything is in this course required. So to understand better this terminology, like or revise this Markov process or multi-arm. Uh, can you give a little bit brief background about this?
Yes. So Markov decision. Markov decision processes is one of the background. Okay, so I understand this. I mean, Markov
Is
chain
it the
is one
same
of.
like yeah Markov chain by like probability chain we
Yes.
make? Is it
Okay,
same?
so no. So Markov chain is a prerequisite for studying Markov decision processes. But if you know Markov chains, that will suffice. I mean, we'll discuss what Markov decision processes is in this course. I mean, in this tutorial itself.
Okay.
And about other prerequisites, I think probability theory is a must. And it will be good if you have some background. So I found that I was muted. Till when
Yes,
did you hear me?
yes. You got muted, so please repeat what you have just said.
Yeah, so I was saying that Markov decision, Markov chain is one of the prerequisites, but in general, if you study probability theory, it will be easier to understand this course. That is one of the main
Yeah,
prerequisites.
I have estimation theory and probability. I have idea, but not in the computer science terminology, like in electrical engineering, with what we studied in that point of view. I have.
That's fine. A course in probability theory is it's sufficient.
Yes.
Okay, so for the time being, let us just remember we are studying finite horizon MDPs. So finite horizon MDPs are expressed as a 5-tuple state space, action space, reward function, a transition kernel. I'll come and explain what all these things are, and an episode duration h. So let me write. This P is called transition probability kernel. And H is called episode duration. Okay, so what are these things that I have not described? Let me describe now. So what is this R? R is again like mu, it's reward function. So I think it makes sense to write it mu as well. Okay, let me change it to mu, because in Bandit this is mu. So here there is something extra, right? Some things are extra. But one basic thing which is extra is the state space. In multi-and bandit, we didn't have any state space. So this reward function here is function of state and action, and it spits out a scalar that is a reward. For example, say this state space is the number 1, 2, 3, 4, 5. Action space is 0 and 1. This is just some mathematical thing, but they can um, denote something physical, some physical things like queue length. So queue controlling is one of the major problem in reinforcement learning or in general in control. So for example, you can think that S is queue length and A is whether you are serving, you are giving service at that particular uh, time instance. So AT will be either 0 or 1, whether you are serving or not serving. Okay, so this instant reward. So you have studied immediate RL, right? So in immediate RL, you are getting a reward instantly. So this mu of 1 comma 0, this is some scalar. Say that scalar is 0.02, like that. So at time t, for taking action taking action at, given your state is st, you will get reward mu st at in expectation. So let me write that in a sentence. At time t, state is st, action taken is at, the received reward is RT, and I'm guessing you know what conditional expectation is, because probability theory is one of the. Someone has a question. Okay. Yeah, Shiba has a question. Please go ahead and ask.
Okay, sir. Thank you, sir. Sir, if the state space is known, then can we say that Markov decision process is the better approach
I
than
don't.
multi-amp matrix?
So I think you have got something wrong. That is, in multi-banded setup, there is no state space. So you are modeling some physical thing in in a mathematical setup that is either multi-banded or Markov decision process. So the setup you are modeling, that has no notion of state. If that is the case, then you can model it as Markov decision process. Sorry, very sorry. Then you can model it as multi-banded. And so if the system has some notion as state, so I have not explained what state is in detail. But if that is a physical object, so for example, what I was just saying, that given the queue length, uh, which takes value from 1 to 5 states, you can take either action whether to serve or not to serve. But for example, say uh, in some uh, in some setup, there is no such state variable. There is no such this queue length, what I'm talking about. There is no queue length. Say you just have to take action based on no just whatever reward you are receiving. There is no state at time t. So for the setups are completely different in two cases. Okay. So state space is, I mean, when there will be a state space, then state space will be known. When there will be not, there will be no state space. Right. So these are two different setups. Is the doubt clear?
Sir,
Maybe
no.
maybe some examples will help. I'll try to give some example after some time. Okay.
Okay, sir. Thank you.
Yeah. Joel has some question. Please go ahead and ask.
Sir, am I audible?
Yes.
Sir, in the multi-arm bandit case, you have defined the reward function as a function from action space to set of real numbers. So, is this a deterministic reward that you're talking about?
No, I am not talking about it is a deterministic reward.
But for
So I didn't say that RT is mu of AT. Did I say that? RT is, yeah, let me write it, what I'm talking. RT is mu of AT. If that is the case, then it is a deterministic thing, right? But I'm not saying that.
Okay.
The basic idea is mu of AT is expectation of RT given AT. So this actually doesn't make much sense. Let me rewrite it. Mu of A is equals to expectation of RT. So RT is a random variable. Okay. RT given at time t, you have taken action A. Is it clear? That's how this mu is defined.
Okay, sir. Yeah, I understood. Thank you.
Right. Okay. So here also I'm trying to say something similar. That is mu of S comma A is expectation RT given AT. First thing is state actually. Given the state, we take action. Given the state, ST equals to S and action equals to A, the reward we receive, expectation of that is mu of Sn. Now the thing is, here there is a prerequisite to understand this blue colored steps in both the columns. You need to understand what is conditional expectation. So, and that is taught in graduate level probability theory course, I think. So please go ahead and search in internet what is conditional expectation. I think there are lots of materials if you do not know. Okay, so reward function we have discussed, and there is another thing P, which is called transition probability kernel. So P is a function from state space, action space, again state space, to 0 to 1, such that sum of S prime is a variable that is evolving on state. I'm sorry, not evolving, wrong term. So S prime is denoting the states. Given any state, any action, and this S prime, this sum of P's, P, S, A, S prime, sum over S prime in state space S is 1. And for all, sorry, for all SA in state action space and PSA S prime is greater than 0 for all SAS prime in S times actions. Okay, so Those who have studied probability, can you guess something? What is P? Why is it suddenly here?
This is the probability.
Plausible? Yeah.
So this is the expected probability for getting the reward state S to S dash.
You said something about reward. So this is not involving any reward. But you have said something S and S prime. Okay. So yeah, it's in that line. Okay. So let me tell that PSA S prime, that is basically probability that ST plus 1 is S prime given at time t, state is S, was S, and we have taken action T. Right? And see that given any S and A, landing into either states in the state space is 1. That is by this condition. And these are all probabilities. And that hence that this quantities has to be greater than equals to 0. Right? So this is what transition kernel is. And so there is nothing much to discuss on bandits today. Now. Yeah. So let me draw something. Say at time t equals to 0, we have state as 0. And then the agent takes action A0 and it
Excuse me.
gives, yes.
That PSAS prime, isn't that incomplete Bayes rule? The right hand side
Incomplete.
seems incomplete. If you apply Bayes rule to that line, there has to be additional term on the right hand side. No?
No. So this is just definition of this transition probability kernel.
No, that PSAS prime equal to probability of ST plus 1 equal to S prime. That statement by Bayes rule is incomplete. No?
So Bayes rule is something else. So you know conditional probability, right?
True. Bayes rule is conditional probability, you know. It seems
Bayes
incomplete
rule,
because
Bayes rule is a relation, right? And conditional probability is something else. So if you know conditional probability, so this probability is basically the conditional probability that given ST and AT or S and A respectively, what is the probability that you are going to land on state S prime at time t plus 1.
I agree,
Okay.
but the left hand side equal to right hand side is probably
This is the definition. This is a definition. So
okay.
Okay. And this P is not defined. I mean, this P is some object and it takes the number, which is the probability. Okay, so at t equals to 0, there is state A0 and the agent takes action A0 and it results in two ways. One is we receive the agent receives the reward. So, okay, the agent receives the reward. So let me write here agent. It receives the reward and the state evolves to S1 according to this probability transition rule or probability transition kernel. Then again, agent takes action A1, receives reward R1, the state evolves to S2. Again, same thing, A2 receives R2, evolves to S3. And now comes this horizon, right? Episode duration, sorry, not horizon. Horizon is something else. Or it is actually called alternatively as horizon, but we'll use the term episode duration. So this continues. State becomes SH minus 1. Action AH minus 1 is taken. Reward RH minus is received. State SH is reached. And there the thing stopped. So this is called Markov decision process. What is the goal? The goal here is maximize T equals to 1 to capital T R T. So these are the two different setups. One has state, another doesn't have state. And there is a particular rule of evolution of the states. And one particular model to represent this evolution of the states is Markov decision processes. There are other models, but this is the most prevalent one where people study RL problems. Now, if you have information about all the things, so state space, action space, you will be knowing, given the this RL problem, that is the most common assumption that you have to know the state space and action space. If the reward function and the probability transition probability kernels are given, then you know. So this is called model. This two things. This reward function and the transition called probability kernel. These two things are called model. Given the model is known, you will not do reinforcement learning. Learning is when you have to learn the model, right? Learn the model or learn how to take optimal actions. Not necessarily you have to learn the model. Without learning the model also, you can do some reinforcement learning. Those are called model-free algorithms, and those are most popular ones. And yeah, so if the model is given, you do not do reinforcement learning. Then what you do is called planning. So design controller given the model. So this is typical optimal control problem where you are trying to maximize certain reward criteria. Okay, so here I have written something very wrong. So this is equals to 1 to H, capital H, not capital T. So yeah, design a controller given the model is called planning, and RL is learning how to control when you do not know the model. And adaptive control is somewhere in between. That says you know some information about the model, but not that is not the exact thing. I mean, you know some range. Okay, so in the next tutorial, I think in some lecture in next 1 2 weeks, this planning algorithms will be discussed. That I'm not sure, but I think it will be discussed. But we'll revise that planning algorithm in the next tutorial. Also, some bandit algorithms will be covered in the next tutorial. Those will also be discussed. And yeah, so that's the agenda in the next lecture. But today, the next we'll discuss what is regret. Is this term discussed in the last week? I mean, week one's lecture?
Yes.
Okay.
During bandit,
In bandit. Yeah. Okay.
yeah, because we got that something called PAC analysis,
What
performance.
analysis?
Uh,
Perfect.
so there, probability approximation. So during that phase, he told something about regret. It is opposite of reward.
Okay.
I mean, whenever an
So
action is taken, instead of getting reward, we were getting some negative values or say feedback from the system, environment. So that is something regret.
negative values as in you are getting reward, right?
Yeah, we are getting reward in place of reward. So uh, if we are not getting positive reward, it means a loss, something like that.
Yeah, I
If
think
you
it
are
was
not
in the
getting
PDF.
positive reward.
It was given that it is the difference between the optimal reward or optimal reward corresponding to optimal action as opposed to the action you took. The difference of that is regret at any given
Right.
time.
Right. Yeah. So that was the right explanation. So you can give different RL algorithms, right? But in theory, how do you prove its efficiency? I mean, how will it perform? Will it perform better than some other algorithm? Will it perform worse than some other algorithm? And I mean, yeah, at the end of the day, you have to evaluate performance of your algorithm if you give some algorithm, right? So regret is one of the notion of efficiency of an algorithm, and that is basically for bandit I am writing. So regret of till time t. Let us also introduce the algorithm. Psi is the algorithm. Okay. So regret of algorithm psi till time capital T is sum of t equals to 1 to t. So what is regret? What does it mean? It means what you couldn't achieve, but you could have achieved. You could have ranked 500 in IIT JEE, but you ranked say 2000. So 100, 1500 is your regret, right? So this mu, the function which is from action space to reals, has a maximizer, right? So the mu star is max of mu A over A entire action space. Now we are assuming that this maximizer exists by some assumption on action space. Say if action space is finite, maximizer will of course exist. If action space is compact and the function mu is continuous, I hope you. I mean, if you're aware of analysis, real analysis at least, then you will be understanding what I'm talking about. If action space is compact and mu is continuous, then the maximizer will exist. So mu star is the best you could have achieved. That is 500 rank in IIT JEE. So mu star that you could have achieved minus what you actually received. What you actually received, that is RT, right?
One question over here is RT could be more than mu star, no? Since it's a stochastic process.
Yeah, actually, right. Very good. But that will actually analyze expected regret. So regret will not analyze. So in expectation, that will be always positive.
Okay. Good.
So this experiment which we are finding temporal in nature, so we will get expected as what we are expecting to be the actual reward.
Sorry, I couldn't understand.
So the experiment which we are performing is a kind of temporal difference learning, and we say
No. Temporal difference learning. I mean, TD learning is what you are talking about. No, TD learning is something very different. I mean, that is an algorithm. So this has no. I mean, what I'm discussing now, regret, that is independent of algorithm. I mean, this is general notion of performance evaluation. So TD learning is a separate algorithm that we'll study. Okay, and this is uh, uh, one evaluation criteria for online learning, to be specific. What does it say? So say you have some algorithm and someone has given you that the regret of this algorithm is t raised to, so let's say psi 1, t raised to 0.75. And you have another algorithm which says regret of this psi 2 algorithm is t raised to 0.5. So which algorithm do you think is better?
Second one,
Yes, why?
because it has a lower regret.
So the question is why lower regret is better,
Because you want to reach the optimality quicker.
right? And there is something else. So you'll reach optimality quicker, but when you will be reaching, then also you'll be taking better actions more. So what it means is t raised to 5, I think will look like this. And t raised to 7.5 will look like this. Maybe. I'm not sure. So while you, I mean, in both of the cases, asymptotically, so what will be the asymptotical regret? I mean, in infinity, you will incur always 0, right? So if you are aware of this small o notation, so these all are small o t. Both are small o t. Small o t, I think it means that, sorry, limit t tends to infinity, small o t by t is 0, right? So both of the cases, this will happen. And in infinity, will incur 0 regret. I mean, the instant regret, I mean, mu star minus RT or mu t in expectation, if it is, if you say, uh, that will be always 0 in infinity. But in finite time, this second algorithm is performing much better because while learning also, it's learning very fast. And that is what this t raised to 0.5 is gaining over t raised to 0.75. So this is called one of the finite time guarantee. Regret is, so regret could be asymptotical regret. I mean, at someone may say that limit t tends to infinity RT of some algorithm is bounded by something, some t raised to some alpha. That is one kind of regret bound, which is called asymptotical regret bound. But that I'm not discussing. That is also a valid guarantee, but it is asymptotic guarantee. But what regret we have defined is finite time guarantee. So if you give an algorithm which has, say, t raised to 0.5 regret guarantee, that means in finite time, you are giving some guarantee that it will learn the system, the multi-arm bandit, so fast. And if someone gives something like log t, and that means that algorithm is better if the other assumptions are same, right? Okay. And then you have studied something called PAC, right? What is the full form? Anyone? Sorry.
Approximately.
Probably.
Probability approximation.
No, no, no. Probably.
Approximately correct.
Yeah.
Approximation correct.
Approximately correct, I think. So this is another kind of finite time guarantee where you say with delta 1 minus delta probability, we will give you an epsilon optimal arm. So I'll discuss what is optimal arm, epsilon optimal arm or action. If we can play some function of epsilon and delta times. So a multi-arm bandit is playing at time 1, I mean starting from time 1, right? It's starting at time 1 and we are playing 2, 3 and so on. Now you have given me two parameters. One is delta, another is epsilon. Delta is probability parameter. So since the system is stochastic, we'll give the guarantees with certain probability, and that probability 1 minus delta. If delta is very small, that means we are giving the guarantee with higher probability, right? So our guarantee will always this f of epsilon and delta, that is some function of epsilon and delta. So if the delta, the vague idea is if we want higher probability guarantee, then we need more samples, more time to play. Now, what is epsilon optimal? An arm is called epsilon optimal if, let me write what denote the arm by A, and arm A is called epsilon optimal if mu of A is greater than mu star minus epsilon. So say this is mu star. No arm has higher reward than mu star. And this is mu A. And this gap is less than epsilon. This gap is less than epsilon. In that case, A is epsilon optimal. So it's closer to epsilon than to the optimal arm, right? So now, if you think intuitively, you are trying to get a very close arm to the optimality. I mean, some arm whose performance is very close to the optimal one. If you want to reduce this epsilon, there is some problem, it seems. I think I'm disconnected from this tab. Let me reconnect. Okay, so if epsilon is smaller, then we can expect that we need more samples to learn to get an arm which has with 1 minus delta probability, we can say this is epsilon optimal. So this kind of this guarantee is for a different type of problem. Here, these are called pure exploration problem or best arm identification problem. So you are not identifying the base term technically. You are saying that we are within epsilon range of the base term. And the idea is f of epsilon delta will increase if epsilon decreases and delta decreases. Either of them decreases or both of them decreases. Right? For example, say for some algorithm, for some setup, epsilon if epsilon delta is greater than 1 by epsilon square delta. And say for another algorithm, if epsilon comma delta is epsilon delta. So which one will be better?
First one.
No, second one, because it needs lesser sample to. So for example, say epsilon is 0.1, delta is also 0.1. How many samples you need to learn the 0.1 suboptimal arm with 0.9 probability at least? In first case, it will be
1,000. Yeah. It's
1,000, right?
lesser than one number.
In this case, it will be 100.
100.
So in the second case, you need 100 samples. In the first case, you need 1,000 samples. So which algorithm is better? Second, right? That is learning much faster. Right? Do you agree with me?
Yes.
So this function provides us a count the number of samples we need to explore.
I couldn't hear. Yes, you will
So
get recording. Someone is asking about recording. Yes. Yeah. Can you please say it more clearly?
like say so this function f epsilon comma delta gives us a lower bound the number of samples we need to explore.
Yes, I'm giving the lower bound because I mean if you have more samples, then you'll of course have. So the sample complex, yeah, you are using the right term, I think. Sample complexity you said, right? So the sample complexity is, I think I'm again disconnected.
These f of numbers you get empirically or they are derived theoretically?
So yeah, this I'm talking about theoretical guarantees. Yeah, so these two one thing is base term identification problem and this regret. Uh, I mean, the algorithm which minimizes regret, that doesn't do good in base term identification problem. The reason is very simple. That is, when you are trying to minimize regret, you are doing a balance between explore and exploit. That means you are exploring new actions. Also, you have to exploit what you have learned so far. because you have a pressure. I mean, the regret performance is always telling you that now also you have to do something better. You cannot just keep your all energy in exploring the actions. Now also you have to do some way you have to keep your performance higher. But the base term identification problem is not saying that. It's saying that, okay, I'll do any kind of exploration. I mean, I will choose any arm. I will not care about the performance in finite time. I mean, I will not care about performance during the play. I'll just say uh, after this many time step, I'll give you the best turn or close to the optimal arm, which has guarantee in two ways. One is uh, it will be this much close to the best turn and with this much probability. So these are two different problems. And for those we have two different types of theoretical guarantees. So people study this two problems a lot, and there are also works which tries to uh, give guarantees in uh, both the paradigm, like base term identification and regret. Okay, so now we'll be discussing some of the last year problems. So we'll just quickly go through this because I have some, like, you can, I think, see I have in the pad there is 4% charge, and for some technical reason I couldn't charge my pad. So we have to finish today's lecture very early. Okay, the first question is, which of the following is not useful approach to standard multi-arm bandit problem with n arms? So this is what exactly what we have discussed now. First option is, how can I ensure best action is the one which is mostly selected at time tends to infinity? So the best action, if that is mostly selected as time tends to infinity, that makes some sense. But let us see other options. How can I ensure the total regret as time tends to infinity is minimal? That's what the regret regret minimization, uh, asymptotical regret minimization is, right? How can I ensure an arm which has an expected reward within a certain threshold of optimal arm is chosen with a probability above is above a certain threshold? So that is also what we have seen as based on identification problem or pack guarantee, right? How can I ensure that when given any two arms, I can select the arm with a higher expected return with a probability above a certain threshold? The problem given is, if you see the question, it's for multi-arm bandit, right? And here you are talking about the option D is talking about when given two arms, you can select higher expected return with probability of certain threshold. So that will not make much sense, right? So you can think that, you see, if you have k arms, you have k arms, so you have to compare these two, and out of these two, whoever will win with, say this one is winning, so this arm and this arm you have to compare again, and so on, and then you can say some arm is better than all of the arm, then you can find the best arm. So that is
Sir,
not making much sense.
so this choosing the arms out of these n arms is up to the agent's choice.
No, it's not the agent choice. It, say Google has a problem. Google is trying to maximize the click-through rate. So Google gives some ads, right? When you search something in the right-hand side of the screen, you'll see some ads. So that is a typical multi-arm bandit problem. So the top ads are basically what Google thinks you are trying to, you will be more likely to hit those ads. Okay. So they try to explore which you are trying to hit more, and based on that, they are learning your behavioral pattern, and that is what they're learning, right? So it's
So,
not Google's choice to choose two of the ads. I mean, if they choose like that, then they will lose revenue. So the model is not like that. If the model is multi-arm bandit, then it's multi-arm bandit. There is, I mean, two-arm setup will not be valid there.
so we are eliminating this choice because two arms are there. So,
Yes, successive elimination is something, there is an algorithm called successive elimination, but that is in reward setup. So here what you are doing is, out of two arms you are, I mean, in multi-arm bandit, uh, I mean, it will add more complexity, right?
I mean, processor, I mean, it's given any two arms. So, given in the sense of what? I mean, what is the meaning in this reference? The question. I mean, that the question itself says that there are n arms. So, what is the assumption in the option of arms?
Sorry, I couldn't understand that.
So, the question is about n arm bandit problem, multi arm bandit.
Yes.
So, what is, I mean, what is the assumption of you of saying there are given any two arms? What is the significance of two arms here? I mean,
There is not such assumption that sorry, there is not such significance. So that's what the thing is. That's why, I mean, this approach is not useful. Does it make sense?
yes, some because it's saying it's given to any two arms. So, given in the sense of what? Is it the agent to decide randomly he's choosing the two arms? And
No,
then
no.
out
So
of
not. So randomness is one thing and arbitrary is one thing. So this is arbitrary. There is, so the word random you cannot use
okay, so yeah,
here.
there's a difference.
Okay, so there are some questions on this Q function of this sort of Q learning type of algorithm in bandit setup. So let's keep those questions. I'll cover them in the next lecture. So I think next lecture will be going to be little longer. So let us come to question 4.
What is the answer for the first question?
D. Okay, so question 4 says that there is one assertion and one reason, and the question is like, does the assertion, the reason is the right reason for the assertion, or is it is not, and which one are true and false. So the assertion is taking exploratory actions is important for RL agents. Yes, it's important, that we have uh, discussed. I mean, for regret minimization also it is important, because otherwise it will not be able to gather enough information to exploit meaningfully. And in best term identification problem also, uh, it is the most important thing. Reason: if the rewards obtained for actions are stochastic, an action which gave a high reward once might give lower reward next time. It is talking about stochasticity of the reward uh, obtaining process. So it's saying that, say you are getting reward I once, and then you are very certain that that will be the optimal earn, but that may not be the case because it may have much lesser expected reward value. Maybe when you have sampled, then you have got higher reward. The problem is the assertion. This reason is not the right reason for the assertion. Why? Because the reason is also correct. I mean, as an independent statement. But why we are exploring is basically to learn this rewards. Yeah, someone has question.
Sir, if we can say that the rewards are deterministic, then there wouldn't be any necessity for exploration.
Yes, right. So
So,
we just do it once. That's it.
yeah, so then reason would be correct explanation for the assertion, right?
No, so okay, so no, it's not actually true what I have said. So if it is a deterministic case, then also you have to visit certain action. I mean, you have to take certain actions at least once, right? So that is also exploration.
Sir, but if we are given the function,
No, we are not given the function. That is the point. So to learn the deterministic reward function, you need to find you need to play that action once at least, right? At that particular run.
yes, sir, yes.
Yeah. So that is the point. Yeah, and that is the answer. Sorry, I think I was trying to tell something else, and yeah. Okay, so let me discuss the last question, and then we'll.
So here reason is the assertion and reason. Well, the reason is the correct explanation for the assertion in this case.
No, no, it is not. So stochasticity is not the reason of exploration. Without stochasticity also, you need to explore. So assertion is right. Reason is also like it states something factual, but reason is not a correct explanation of the assertion. B, I think. Yeah.
So, sir, we can say that reason is like for just a specific kind of models. I mean, but the assertion is a more general reason for exploration.
Sorry, I couldn't
Sir,
understand.
the reason is only for mainly for those models which have stochastic outcomes, whose data is, I mean, who have stochastic outcomes for the actions. Reason is
No,
more specific in nature, but the assertion is more general in nature of exploration.
no. So the reason has to be reason of the assertion in every setup, right?
Yes, sir, that's correct. So the reason is more specific in its outlook right now. So it is assuming that the stochastic.
Okay. Yeah. So reason is in for much specific setup, right? Yes. But the thing is, for deterministic reward function also, you need to take exploratory actions. So the reason is not right reason for the assertion, isn't it? Yeah. Any doubt? Okay, may I move to the next question, 5? So we are trying different algorithms to find optimal arm, and we are plotting payoff versus time, expected payoff versus time. So it is not exactly regret. So here it is mu t expected. That's why I'm writing mu, or we can also write RT given AT and T. So first one is tan H. So tan inverse looks something like this, right? So tan inverse 1 is, sorry, tan inverse infinity is pi by 2, right? I don't know. It should be, I think, normalized. Then 1 minus.
In the assignment, they have actually given the diagram.
Is it also given in this year's assignment?
Yeah,
Yes,
yeah,
sir.
they've
Yes,
given the plots.
Oh, then I should not discuss. Okay, so okay, then you solve this.
Oh, I'm sorry. I shouldn't have said that.
Anyway, I think I can give the hint. You just integrate it, right? That's it. Okay, so here I have 1% charge in my pad. So here I have to stop today's session. Yeah, very nice questions I have got from you guys. Hope this will continue. And if you have any feedback, you can write me in my mail. So I'm writing my mail ID here. And if you have anything specific to discuss, that also you can write.
Sir, from where can access these live lecture recordings?
Sorry, come again.
Sir, from where can we access these live lecture recordings?
Okay, that I do not know exactly because I'm not part of this like administrative team, but I'll ask. And so I mean I have to upload in YouTube, but how to broadcast that I'm not sure. I think they will post it, but if they do not, then I'll take care of it. Maybe I'll post it in the group.
Okay.
Thank you. Thank you very
Okay.
much, sir. It was wonderful.
Yeah. Thank you. Thank you.
Thank you.